in this course, we're going to learn about that data and the ideas that we have built up around the data to try to make sense of it, to try to understand it. Let me give you an analogy so that you can get the sense, as I do, that this idea of atoms and subatomic particles is really well understood. There's another scientific idea that these Greek philosophers debated, which was our place in the universe. A very different question. For instance, do we live on a flat Earth, or is it a ball? Are we the center of the universe, or is something else the center, or is there no center? Okay, these were all legitimate questions for people to be asking and to be curious about. And again, there were different philosophical camps 2,500 years ago, and there were in fact Greek philosophers who believed a contemporary version of the way the world works, but they weren't really collecting data and making measurements, watching the planets move through the night sky, and it really took 2,000 years to the Renaissance and afterwards for people to begin to make definite statements. And today, we all have this worldview. It's taught to us as little children in elementary school that the sun is at the center of the solar system and the planets go around in orbits around it, and we can make sense of a phenomena like, for instance, that the sun rises in the east, travels across the sky and sets in the west, without invoking this kind of primitive idea that we're at rest and the sun is going around us once a day. Okay, I think we can say with conviction that that's not a scientifically valid idea, and I think pretty much everybody will agree with me. If you disagree with me, it's worth thinking about why we know that, and even if you do agree with me, it's worth asking yourself, how do you know? Why is it that you believe this picture that was given to you, handed to you by your elementary school teachers, that it's not the case that the sun is rotating around the earth once a day? There are many good reasons to believe that. There's lots of data. There are many experiments and measurements that you can make. In fact, even ones that you could really make. And it's fun to think about. And it's something we're going to think about throughout this course. When I tell you about scientific facts, these facts are all based on evidence, and you should always be asking yourself, how do I know? Why do I believe that? The goal of this course, then, is to give you the framework. It's much like this framework where I could describe the solar system and you could have a mental model. And once you have a mental model of the solar system, you could understand news reports about satellites in orbit around the Earth or rocket ships heading out towards Saturn to explore it. You have a mental model, a framework into which you can fit contemporary ideas and explorations and discoveries and make sense of them. And what I would like to do is to give you such a mental framework to understand the contemporary ideas that we have about particle physics, about the fundamental building blocks. It's a model which is not so common, although I think lots of people do have some idea, some crude, intuitive sense given to us in our elementary school and through high school training about what an atom is. But we're going to go deeper. We're going to look beyond atoms and ask what they're made of, and what they're made of is made of, and we're going to follow this chain as far as we can. Particle physics' goal is to try to get to the bottom. And this leads me to an idea. It's a kind of a philosophical idea, an approach to understanding the world, which I call reductionism. Actually, everybody calls it reductionism. It's the idea that when you look at something complicated, there are many ways to try to understand it. And one of the ways is to try to ask, what is it made of? What are the kind of more universal building blocks? That's a reductionistic approach because it reduces a complicated thing to a simple thing. Now, this is not the only way to approach science. If you're looking at human beings interacting with one another, and you say, what's going on? How do I understand the conflicts and the discussions, human psychology or sociology? You could, in principle, think about that by investigating human beings and looking at various aspects of their interactions. Or you could be a reductionist and say, let me study the human brain, and let me try to understand human behavior in terms of the chemical and physical makeup of the brain. Now, it's certainly not the only way to understand human behavior, but I would argue it's a useful way. We can come up with drugs, perhaps, if somebody is dysfunctional. In some cases, it really does boil down to a chemical imbalance. In other cases, it requires psychotherapy, right? There's lots of possible approaches that you could imagine. The reductionist one being only one of many, but a very powerful one. If you ask a doctor, how does the human body work, especially a sort of a Western doctor, I think their approach is to a large extent reductionistic. They say, well, the human body is a collection of organs, and those organs are fairly universal. People have hearts, and dogs have hearts, and worms have hearts, and so we can understand complicated systems in terms of the fundamental building blocks and how they fit together. You got a heart and lungs and bones and skin, and we need to understand not just what those parts are, but how they hook together. Now, that's not the only approach to medicine, and it may ultimately just be one of many useful approaches, but I think we can argue that it's definitely a useful, valuable scientific approach to do that, to think reductively. And as a physicist, I think we tend to think reductively to deeper and deeper levels. I mean, what's a heart? What is a heart? How does it work? Well, to me, the way a heart works primarily is it's made of a bunch of cells of a certain type, and they have a certain structure, and they interact with one another in well-defined ways. So again, I understand this complicated thing by reducing it to its components and how they fit together. And we can keep asking that question, okay, what's a cell? How does it work? Why does a cell behave the way it does? And the answer is, at least one answer is, well, a cell is made of various protein molecules which fit together in a certain configuration. Great. So what's a protein molecule? Well, it's a bunch of atoms, hydrogen and carbon and nitrogen and oxygen and whatever it is that makes up a protein molecule, fitting together in a certain way, obeying certain rules. So we keep understanding complicated things in terms of simpler ones, which are more universal. By the time we get down to these atoms that make up the molecules, these atoms are constituents of everything in the world. So if you understand how they work in a protein, you also understand how they work in the frame of a car. So there is an appeal and a value to following this reductionist approach, even if it's not the only way. Particle physicists just ask, how far can we go? We've got these atoms. What are they? Well, now we have a mental model. They're made of a nucleus and electrons which orbit around it. It's a kind of a classical picture which we will be talking about in future lectures in this course. And then we can ask, okay, what's the nucleus made of? And we understand it in terms of smaller particles still, protons and neutrons, which themselves are made of something called quarks, a bizarre word which we're going to be learning lots about. So anything that's unfamiliar at the beginning of this course, hang on. We're going to be defining what's a quark and what's an electron and what's a lepton, and all the buzzwords of this field are going to make sense because it's really just a simple story. And in order to make sense of them, it's nice to have some mental framework, some model, and that model can be quite simplistic. It's perfectly legitimate to have a kind of a naive view to start with that gives you the essence of the story. I have to make an apology for reductionism because there's lots of discussion in the scientific communities about how useful and how important reductionism is. For example, supposing I want to teach you about music. I say, I want to understand Mozart. There are various approaches, and one approach might be to sit down at a piano, listen to the Mozart music, and figure out what the individual notes are that I'm hearing. I might write them down on a piece of paper with some lines using a scientific notation to encode which notes the music is made of, how long they last, and how loud or soft they are. Of course, that's the way musicians get the music. A pianist sits down and reads that notation and can play Mozart. So basically, as a reductionist, I've said Mozart is just 88 notes on a piano. I have reduced music to the simple fundamental building blocks, those 88 keys, and then the various properties they can have, how loud and soft, how long they last. That's a reductionist approach, and of course it's not completely satisfying. It's not just the names of the notes and the order. There's something deeper about Mozart's music that's compelling and beautiful, and so there's more to understanding the music than just knowing the notes, but clearly knowing the notes is useful and important and valuable. So this is where we're headed. We're going to be learning about the building blocks and how they fit together. But let me also, in this first lecture, before going into any of those details, which comes later in this course, ask the kind of big question, why is it that we care? I can't just give you a hard and fast answer to that question. It's perfectly legitimate. people will ask you, why are you